Well, welcome to Chapter 7 overview. We're going to be working on confidence intervals. For most of them, I'm going to be using the calculator, and actually the rest of the semester I would be using the calculator to make them, but for this first one, I'm going to use the formula, and then I'll show you how to do it with the calculator. So the average height for this sample of 30 men, we have n equals 30, x bar equals 70.1, and the standard deviation, since it's a sample, we use the letter S for standard deviation, 1.9. Now the idea is, wherever these people came from, it doesn't say, but whatever the population is that they represent, then we would think that, on average, guys there are 70.1 inches tall. So what is that? 5 foot 10, about 5 foot 10. Anyway, but of course, since that's based only on 30 people, that's not going to be perfectly true. So first of all, we say that the point estimate is 70.1. In other words, if I had to estimate what's the average height of everybody, I'll say that it's going to be 70.1. But the thing is, there's going to be some error. And the error is going to be, well, first of all, when we're talking about means, then for the critical values, they're called, you can either use the z table or the t table. Well, which one do you use? Well, if this sample information is all you know for the standard deviation, then we're going to be using the t table. So that's table A3. Hey, that may be your first time using table A3. What an exciting day. Anyway, then the formula goes, all right, take what's called the critical value from table A3, and then the standard deviation divided by the square root of n. And then that will tell you how much this estimate is off, the error. Okay, now what about table A3? So, table A3, or the t-distribution, looks like this. First thing you do when using this table is decide, is there going to be one tail or two? Since we're making a confidence interval, or in other words, what we're going to say is, at the end, the mean is between this number and this number. So it's going to be, you take 70 and then add the error, and that's going to go over here. But maybe you should subtract the error. So take 70.1, subtract the error. So in other words, we've had two tails. The next thing to do is decide how much is the alpha. In this problem, I said to use 95% level of confidence. So you subtract from 100, that leaves 5%. So that's what alpha is equal to. So we're going to use this one right here. Once you've decided that it's going to be two tails and it's going to be 0.05, that means we're using this column. The only other thing to do is figure out degrees of freedom. And degrees of freedom, it's simply the sample size minus 1. So for us, that's going to be a 29. So you go down the middle column until you get to 29, and there we have it. So in other words, it can be off by approximately 2 standard deviations, 2.045. So that's what we use right here. The alpha over 2 means that you've got the alpha and then you're divided into two tails. So this was 2.045. The standard deviation, 1.9, divided by the square root of 30. And I don't want to show off calculating that in my head right now, so I'll just use the calculator. 2.045 times 1.9 divided by the square root of 30 people. So it's saying, okay, if you say that they are 70.1 inches tall, you could be off by as much as 0.709 of an inch. So it could be that they're actually taller than that, taller than the 70.1. So on this side, you add the 0.709. On this side, it could be that they're shorter. So take 70.1 and subtract the error. All right, so 70.1 plus the error of 0.709. So they might be as tall as 70.809. Take 70.1, subtract 0.709. They might be as short on average as 69.391. And there is our first confidence interval. Then, as I promised, usually we're not going to be using the formula, we're going to be using the calculator. So how do you do that? You just need this given information over here, and then you go to Stat, move over here to Tests, and there's a whole bunch of things that the calculator does for us from this point on in the semester. So these tests, that's chapter 8 and chapter 9. What we need is down here the interval. And as I said, there's a choice of Z or T. Since this is the S for standard deviation, then we're going to be using the T table. If this was the sigma, or in other words, the standard deviation for the whole population, then we would be using the Z. But S means T. And you could either have the data in a list, like list 1, or you could type in the statistics yourself. So I'll do that. The X bar, 70.1. The S, 1.9. Sample size of 30. The confidence level is 95%. And then calculate, and you'll notice that 70.809 on the right side, so we got that one right, and 69.391 on the other side. Perfect, what a smart calculator. Okay, the next kind of interval. So this one is about proportions. So in other words, this is saying the proportion of people that claim Christianity as their religion is between what and what. Did you notice I'm doing my part to protect the environment by recycling an old problem? Or actually reusing. Anyway, we've got the X equals 116 of them say that Christianity is their religion. The sample size is 150. Or in other words, what percent is that? 116 out of 150. So when we're talking about the mean, there's two different symbols. It's X bar if it's a sample, and it's mu if it were the whole population. Mu. When we're talking about proportions, it's going to be p hat if it is just the sample, and then it's p for the whole population. So, like I said, now we're going to use the calculator rather than the formulas. So you go to Stat, Tests, move down until you see a proportion interval. There it is. It's the 11th one down, A, letter A. One proportion, Z interval. And whenever it's proportions, you have no choice. It's always going to be Z. Everything about proportions is Z, or table A2. Then you just need to tell it how many people out of the sample size, what confidence level you want. This time I asked for 98% confidence, and then calculate. So it says, you don't want it in the glare. So it says that it is 0.773 is the point estimate for the proportion, but it could be anywhere between 0.694 and 0.853. And that's it for that one. So There's the given information. Create a 95% confidence interval for the mean IQ. Okay, so one thing I was looking for is this. Because confidence intervals in this chapter can be about the mean, could be about proportion, or could be about standard deviation. So the first thing I had to find out is that it's about the mean. So that means it's supposed to look like this, the final answer. The next thing is, when it's about the mean, there's a choice. It's either going to be the z table or the t table. And because of this, then I use the z. So then I write down my given information, and that is that the sample size is 56. The x bar, or average for those people, is 114.7. And the overall standard deviation for the whole population is 15. So that means that we're going to be using the z interval. This one, number 7. So notice that it has the sigma. So sigma equals 15. The x bar, 114.7, based on 56 people. And then the confidence level, 95%. By the way, in the future, there are going to be times when this is left off. And if it's ever left off, then as a default, you go ahead and use 95% confidence. All right, then go to calculate. And it says, okay, the average IQ is somewhere between 110.77 and 118.63. Then on to number 4. Trying to get it on the page. There we go. Pretty much. So Kobe Bryant played 78, so I can already write that down. N equals 78 games. He averaged, so that's an X bar, 27.4 points per game. And then since that is not his whole population of all the games he's ever played, then it's S. S equals 7.5. And then this is for Kobe Bryant. For his 15-year career, so I cannot write that down as an N, because my N stands for how many games he played. Over the 15 years, I don't know how many games he played. Michael Jordan, he averaged this, and it says nothing about the standard deviation. So I don't have this type of information about Michael Jordan. So what I have to do is make a confidence interval for Kobe Bryant based on this information over here, and then see, does that interval surpass Michael Jordan's 30.1, or does Michael Jordan's 30.1 surpass Kobe Bryant? Let's see. So keep in mind this interval is for Kobe Bryant. So the mean is between what and what? So we use the t interval, again because this is the sample standard deviation S, so we need to use t interval. Stat, the t interval, then the average, 27.4, the S, 7.5, based on 78 basketball games. That was for last season, 2002, 2012, 2013. And then use 95%. So that means that Kobe, throughout his lifetime average should be somewhere between these two numbers. That's with the assumption that he continued to play the way that he played during that season. Anyway, so this interval is saying, you know what, I'm 95% sure that at the best, Kobe's barely going to make it to 29. So, who's better? Well, as far as scoring points, then Michael Jordan's better because over his lifetime career, he averaged 30.1. The very best that Kobe could do is 29.09. So it looks like Michael Jordan is better at, or actually was better than Kobe is, details, was better at scoring than Kobe Bryant. Yeah, well, they're still both billionaires. Anyway, on to the next one. So when an exam has 100 points, the standard deviation should be 15. But I had this superb calculus class last semester. The first test, 40 people. The average, a phenomenal 80.1 for the first test. Standard deviation, sort of small. Should be 15. So then make a confidence interval about the standard deviation. So this one, unfortunately, is not in the calculator. This one goes like this. The standard deviation squared is going to be sandwiched between these two fractions. First of all, you use n minus 1, or in other words, degrees of freedom, and the sample standard deviation squared. And that's true on both sides. Then we're going to use table A4. What an exciting day, a new table. Woo! We're going to use table A4, which is called the chi-squared distribution. So it's like a big fancy swirly X, but it's called chi-squared. And there is a chi-squared right and a chi-squared left. On the right side, we divide by chi-squared left. On the left side, we divide by chi-squared right. I'll explain why when we get the actual numbers. So we now need table A4. Mine's a little bit messy, but this is table A4. So, like I said, there's chi-squared right and chi-squared left. So what I do is I just divide the table right down the middle. Chi-squared right is going to come from the right side. Chi-squared left is going to come from the left side. And notice that these numbers match up. 10% and 90% make 100, so those go together. So this one would give you chi-squared right. This one would give you chi-squared left. And then 5% goes with 95%, etc. These match up. 1% with 99, etc. So, the other thing we need is degrees of freedom. But as you remember, that's easy, that's n minus 1. So degrees of freedom equals 39. So we're using 95%, which means that you have to take the alpha, which equals 5%, and cut it in half. Half of it goes to the right side, half of it goes to the left side. So if you take 5% and cut it in half, that would be this number. So that means we're going to be using these two columns, chi-squared right, chi-squared left, and degrees of freedom of 39. When you look over here for degrees of freedom 39, there is no 39. And in these tables, whenever they don't have what you want or need, then you use what's closest. So the closest to 39 is 40. Then what I usually do is right here, I couldn't use a 39, I had to use a 40. So if we're using 40, and if I follow this one down, and I'm going to just do chi-squared right first, follow this one down, and it is to 40, then that value is 59.342. 59.342. Then this would be degrees of freedom 39 and the standard deviation squared. So now we need chi-squared left that goes over here. So that's going to be this column and go down to the 40. So that's right here at 24.433. And the reason for the whole chi-squared left goes on the right and chi-squared right goes on the left is because right here you put the bigger number on this side so that when you divide by the bigger number, it puts the smaller result here. When you divide by a smaller number, it puts the bigger result right here. Then, since we need to solve for the sigma, we have to get rid of the square. So, take the square root of both sides. And then, use a calculator. So, it's going to be the square root, then there's a 39 times a 10.5, which is squared. And then it's divided, I'll just do this one right now, divided by 24.433. So this side is 13.266. Now for the other side, I'm just going to get the problem back again, and all I have to do is change this value on the bottom to 59.342. So 8.512 on the other side. 8.512. So in other words, for that particular calculus class, the standard deviation on tests is probably somewhere between 8.5 and 13. So that means that no, the 15 is not possible. It does not land in the interval. And that's it. That's chapter 7.